One thing that's extremely important as you begin to analyze motion and deal with these parameters like x, v, and a are the signs that these parameters can have. And by signs, I mean, yes, the positive or negative sign that can be attached to any one of the items. And the reason why signs are so important is because invariably these quantities that you're dealing with will get put into equations. For instance, we know that x equals to x naught plus v0 delta t plus 1/2 a delta t squared. This is an equation. And v would go into equations. V is equal to v naught plus a times delta t, something like that. These can be put in an equation and evaluated with a computer or a calculator. And certainly, if you have different signs floating around on these parameters here, very drastically different results can pop up. For instance, here, it says that a new x is equal to the current x position plus v naught times delta t. Now, delta t's will always be positive in these videos, in this class, and so on. So that will always be a positive number. But suppose v naught was negative. Then as you go through the calculation, you'd have x equal to x naught minus v naught delta t. This whole term would become negative if v naught was negative. You have a drastically different answer than if this quantity was positive. The same thing goes in this acceleration term right here. This is a plus a delta t squared. Now, half is always positive, and delta t is always positive, and you square it, it'll always be positive, once again. But a can be negative. So if a had a negative value on it, you could get this whole term being subtracted from whatever sort of number sequence you happen to be evaluating the equation, so you have to be very careful about that. So the question is, what do the signs mean, and how do I know what sign to put on a particular object? Well, in order to get the meaning of the signs down, we just go back to grade school. We think of our good old Cartesian coordinate system, which looks like this, where right is positive, left is negative, up is positive, and down is negative. That's the way you remember plotting points, say, in maybe your first algebra or geometry class, something like that. We'll stick to the sign convention here in sort of university level physics even, and we'll just assign it this way. Anything going right is going to be positive. Anything going left is going to be negative. Anything going up is positive. Anything going down is going to be negative. We'll stick to that sign convention. So the question is now is, what does this really mean for us here? Well, here's an example right here of a car. A lot of cars in physics and stuff. It's kind of a weird looking car, but suppose it's moving this way at 10 meters per second. The 10 meters per second refers to, say, the current velocity of the car. So as I was going to work a problem about this, I would definitely put in v naught to be positive 10 meters per second. And I got the positive because the car is moving towards the right. That's how I got it. In another example, you could have a car that's, say, moving this way. I'll go ahead and draw another car here. Something like that, maybe a truck, and it happens to be moving this way at 3 meters per second. If I was going to put that 3 meters per second into any equation at all, the v naught for this would be minus 3 meters per second. And there's a classic example right there where the 3 meters per second could make a huge difference on answers, because if you put a positive 3 in here, you're not mathematically reflecting that the car is moving towards the left. The positive 3 would be if it was moving towards the right, but in this problem it is moving towards the left, so you better have a minus sign in there. And that's what I mean by these sign conventions sort of affecting things, and that's a big deal as far as this equation goes. So what I'd like to do then is just wrap this particular video up by making a table to show you what these different sign combinations can do. So we'll make a little table here. That'll be the sign of V, the sign of A. We'll sort of have a picture here. And then we'll describe what action we would expect from that combination of signs. And there's 4 of them. So make a little table like this. Here you go. Something like this. And off you go. Okay? So suppose V was positive and A was positive. A positive V means the object's moving towards the right. A positive A means the acceleration is also towards the right. So what you'd expect then if you had a ball or something like this is you'd have a V pointing this way, and you'd also have an A pointing this way. They don't have to be the same size arrows the way I'm drawing them. They're different quantities, but the point is that they're both pointing towards the right. And what you'd expect from this sort of action, if you have a velocity and acceleration in the same direction, the object will always be speeding up. That's just the way that works. The A is in the same direction as V. The A will work to build V up, and it will be speeding up. An identical case can occur only in the other direction if V and A are both negative. So if V is negative, it points towards the left, because left is negative according to our sign convention. If A is negative, it also points towards the left. So the drawing that you'd get would be a figure like this. The V is that way, and A is that way. They both point in the left direction because they're both negative. The object will also be speeding up. The difference between the two is this one will be speeding up towards the right, this one will be speeding up towards the left. So they're both speeding up, but in different directions because of the different signs that they have. The other combination is suppose A is positive and, V is positive and A is negative. You'd have a system like this, a ball or a car or something, where V is definitely pointing this way, because that's positive, and A would be pointing that way, because that's the negative direction here. So whenever V and A have opposite signs like that, you have the V that's trying to go right, but an A which is tugging it and slowing and making it smaller. This object here is going to be slowing down. They have to. Whenever V and A have opposite signs, the object will always be slowing down. And of course, the other case is just the opposite signs. Now V has gone negative. So V is pointing to the left, A is pointing to the right. So here's a V pointing to the left. Here's an A pointing to the right. Again, we have a case where V and A oppose each other. This object will also be slowing down. Again, slight difference between the two here. This will be moving to the right but slowing down. This will be moving to the left and slowing down. And so those are the four combinations of signs that you can expect. And the reason why the signs are so important, once again, is to tell the equations what direction something's moving in. So these signs that you put in front of the V's here are very important. I'll just sort of conclude here by saying to mathematically give direction, or give directions. It's a way of telling the equations what actual direction something is moving in so they can spit out the right answers. Because, for instance, if you have a V and A that are in the same direction, you have the same sign, as in this case right here, you'd really like the new V to be larger than that V right there because the object is speeding up. You've got to get the signs right. Or in this case right here, if the object is slowing down, if you use an equation to calculate the V at a small time in the future, you'd really like that V to be a little bit smaller than this V right here because the object is slowing down. Again, a V one way and the other, the new V at small time in the future should be smaller, and you need the equations to give them a chance to allow you to do that. So that's what these signs are for here, mathematically giving the equation some direction in there.